So now to do backprop, we need to learn a little bit of so-called vector calculus. The word sounds fancy, vector calculus, but the concept is really easy. Let me show you. There are two things we need to know about. We need to know about this so-called gradient, and we need to know about this so-called Jacobian. And the idea in a nutshell is really simple. First, I will read it out and then I'll explain it. So let X be a n-dimensional column vector, right? It belongs to this set of r to the power n, which essentially means our X is a n-dimensional column vector, right? So it's n cross 1. And let f be a function that takes in this n-dimensional column vector and gives us a real number, right? So let f be a function that takes in this x, and what does it give? It gives a real number, right? It gives us a scalar. So let's say it gives us some s, yes, and this s belongs to r, like we have written here. So f essentially takes this x, right, which is n-dimensional real vector, and gives us a real number. Now if we were to differentiate this, so the derivative of f, if we were to differentiate it with respect to the input, the vector x, right, this is what the gradient looks like. And all it is saying is that I will collect all my, all my partial derivatives of f with the components of x in this row vector. Meaning, suppose what we want to do is we have this, so the output is of course a real number, but now we want to differentiate it with components of x, right. So let's say this is our column vector x, and this is made up of a few components, and we call it x1, x2 and so on, all the way to xn, and we collect it in a row vector, and we call this a gradient. So this df by dx is called the gradient of f, and what it means is it is essentially this row vector which looks like dou f by dou x1, dou f by dou x2 and so on. Yeah. So can we now think of a function which looks like this? I will show you a few examples. For example, one of the functions could be something like the mean square error or the cross entropy error, right? So loss happens to be such a function which takes in, let's say, a vector. Let's say it takes in x. It also takes in O, but O is a constant. So let's say, or T, which is a constant, but let's say it takes in something and it gives out a scalar. Yeah. And we want to differentiate it with respect to x. And this is what differentiation of the loss with respect to, say, the output will look like, right? Because what is the loss function of? So the loss is a function of, so the loss, what is the loss a function of? The loss is a function of your output and the ground truth, the target, right? Now target in this case is a constant. So the only thing that we can differentiate it with respect to is our output. So we can differentiate so we can find the derivative of, so the gradient of the loss with respect to output. And what will it look like? It will look like this row vector, which will have your partial derivative of loss with respect to the first component of output, O1, then partial derivative of loss with respect to the second component of output, O2, all the way to partial derivative of loss with respect to the last component of output, On. Yes, so it's simple, and I think it will get clear when we actually do a concrete example, and we'll do a bunch because we will do it for each of these layers. Okay. Now, kind of making this a little bit more general, loss was a special function that took in a vector and gave out a scalar. But you can always have a more generic function. Let's say now we have a function f that takes in now a vector, but it also gives out a vector, right? Let's say it gives out something like L, right? And it gives out a vector which is L. So in this case, if you want to then kind of know, okay, how will my the function change when we differentiate it with respect to input, it will basically give us, okay, how will say this L, the output, change as we change our input, and it will give us a combination of how will each component of output change as we change the component of input. How will my so if I wiggle a little bit of my input, my X, how will that component of L change? And we can represent that change with respect with this so-called Jacobian matrix. And what is this Jacobian matrix? So let me just read it out first. So let X be a n-dimensional vector like earlier, a column vector, and let F be this function which takes in this n-dimensional vector, right, and gives out this m-dimensional vector. Now this derivative of F with respect to X is this m cross n matrix. And what does this matrix look like? The first row is essentially the gradient, right? It basically generalizes it. This is a special case of this. If the dimension of output, if m is equal to 1 here, then it boils down to the gradient. So what am I saying? The first, because my F has only one component, right? So what are we saying? Our X, so F takes in this vector, and what is our X looking like? X looks like a vector of size n cross 1. And then what is F? F is again a vector of size m cross 1. So what is this first component? We call it F1 of X, right? So this is what we are so let's write it differently. Let's call it Fx of 1. And what is the first component of X? We call it X1 all the way to Xn. So what will this Jacobian matrix look like? It will, the first the first element of this Jacobian matrix would be Fx1 derivative, so partial derivative of with respect to X1. So the column, it will all be respect to this, right? So it will be still d of dou of x1, but with the last component of my input. So what does it mean? It will tell me, okay, so what does this mean? It means how much will my output change, this component of my output change if I wiggle this component of my input. Similarly, basically show, okay, see how much will again this component change if I wiggle the last component of my input, because it's dou fx1 by xn. And similarly, the second row will essentially tell me how much will the second component of my output change as I wiggle the different components of my input, because it will correspond to dou f x2 by first x1, then dou f x still 2 because the whole row is 2 by x2, and so on. So the Jacobian essentially is a collection of all these partial derivatives, and what does it show? It's a combination, right? It's a combination of this m cross n, and we put it in a matrix, and it shows how much will my output change, or that component of output change as I wiggle my input, and each component of output corresponds to one row, right? So the first row shows how much will my output change as I wiggle my different components of my input. So how much will my first component of output change as I wiggle the different components of my input. What does the last row of my Jacobian matrix show? It shows, okay, how much will the last component of my output change as I wiggle the different components of my input. And that is it. That is all that there is for Jacobians and gradients.